We're now going to talk about how we can find the finite sum of a geometric sequence or series. And the way that we do this is that we start with the fact that by definition Sn is going to be equal to a1 to an, but this is going to be equal to a1 r, now it's just going to be a1 plus a1r plus a1 r squared plus a1 r cubed plus dot 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 all the way down to an. Well, I can multiply both sides by the same thing, and that gives me r of Sn, which is a1r plus a1r squared plus a1r cubed plus a1r to the fourth plus all the way up to anr. Well, now we're going to do Sn minus rsn, and notice that that term is going to subtract, that's going to subtract, and this is going to happen all the way down, and this term will subtract, so that what we have is a1 plus, or rather minus, an to the r, and an to the r is a1 times r to the n minus 1 times r, which when we multiply those together just gives us r to the n. Well, I can factor out an Sn here, which is 1 minus r, and I factor out an a1 here, which leaves 1 minus r to the n, and so my sum is equal to the first term times the 1 minus r to the n divided by 1 minus r, and this will work for any partial sum, anytime we're only summing the first n terms. And so let's look at a particular example. Suppose I tell you to sum from I equals 1 to 17, 3 times 0.4 to the I. So here's a1, we pull that to the outside if we wanted. Here's r, and n is the 17. So S17 is equal to a1, which is 3, times 1 minus r, which is 0.4, raised to the 17th, divided by 1 minus 0.4. Now we're going to plug this into our calculator, so 3 times the quantity, 1 minus 0.4 raised to the 17th power, divided by 1 minus 0.4 equals. And it looks like these first few terms add up to approximately 4.9999. Need 2 more 9s, so it doesn't round. So it gets really, really, really close to 5.0. But the first 17 terms are going to add up to this number right here. And that's how we perform a finite sum.